Hi folks, welcome back. I hope you're all doing well. Today I want to take a look at a paper from the upcoming OSDI conference. That's the Operating Systems Design and Implementation Conference, which is happening, I believe, in early November. This paper talks about the design and implementation of a Java virtual machine that can run unmodified Java applications on a disaggregated data center architecture. So right off the bat, let's first talk about what resource disaggregation means. Now, typically in large data centers, traditionally you would have typical servers where each server has a lot of CPU, a lot of RAM, a lot of storage. But in the last few years, people have been investigating a new kind of data center architecture where you try to isolate individual resource types to specific servers. So for example, you would have a bunch of servers that have very capable CPUs, but very little storage and RAM. And then you would have a bunch of servers with a lot of RAM, but perhaps only mediocre CPUs and storage. And finally, you would have a lot of servers that have a ton of storage, but only a little bit of RAM and only mediocre CPUs. So the idea is to have servers that specialize and provide just a certain kind of resource, whether that is CPU or RAM or storage. Why would you want to do this? What is the advantage to organizing your data center like this? The biggest one by far, and this is what impacts the economics of the data center, is that you get much better resource utilization. When you have traditional servers, each with a lot of RAM, a lot of CPU, a lot of storage, you have to play this very complex multi-dimensional game of Tetris or bin fitting to allocate your jobs across your servers such that you're making the best of your RAM and CPU and storage. Whereas if you disaggregate your resources, you don't have to play this game of Tetris anymore. You have one pool of servers which just have a lot of CPU. You have another pool of servers that just have a lot of RAM. You don't have to find one specific machine that has just the right amount of CPU and just the right amount of RAM for your application. You also get better failure modes because if a certain kind of server dies, it doesn't take out a bunch of CPU and RAM and storage. It just takes out the kind of resource that that server was providing. So if one of your RAM server dies, it doesn't affect a lot how much compute you have. It only affects how much RAM you have. And finally, it gives you much more elasticity when designing your data center. If you decide you need more RAM, you just add more of your memory servers. If you decide you need more CPU, you just add more servers with powerful CPUs, as opposed to adding traditional machines which have a lot of everything. That sounds all well and good, but then the question is, how do you take an application that's designed to run on one machine and run under the assumption that it has access to all kinds of resources, whether it's compute or storage or memory, and then run it on a disaggregated architecture? Especially if you think of applications that run in a managed runtime like the JVM, where the runtime is tightly integrated with a garbage collector. The simplest or the most brute force way of doing this would be to utilize RDMA, or Remote Direct Memory Access. What is DMA? DMA is when an I/O peripheral can read or write to RAM directly without going through CPU. The main idea is to save CPU cycles when doing intensive I/O. RDMA, or Remote DMA, is the same thing except that now you're doing DMA to RAM on a remote machine over a very fast network. So you could just treat the memory in all these remote machines in a disaggregated data center as being accessed over RDMA. The problem with doing that is that your performance would be terrible because you'd be making these remote hops for memory very frequently. And obviously the latency of that is going to be much slower than the latency of accessing local RAM. What you really want to do is consider the runtime semantics of the program you're running. or of the managed runtime that you are running, and then design a system that optimizes those memory access patterns. And that is exactly what the authors in this paper are trying to do by trying to design a JVM plus underlying swap mechanisms in the operating system such that they can make the best use of this disaggregated architecture. What is the challenge in doing this? Why is this a difficult problem? It's difficult because garbage collection by its very nature traces your entire object tree. So it's doing a lot of non-localized memory accesses over your entire heap. So there's very little locality of reference in a garbage collection access pattern. One of the key insights of this paper is that to turn garbage collection into a problem where you can exploit locality, the authors are proposing that you offload most of this GC computation to the memory servers themselves. Now, garbage collection is mostly a memory-intensive operation and does not use a lot of CPU. So it's a perfect fit for these memory servers which have a ton of RAM but only mediocre compute power. The authors are assuming that each application that's running on the JVM still runs on a single compute server. So they're not splitting the computation out to multiple compute servers. However, an application running on a single compute server is able to access memory from multiple memory servers. Now, they are able to run unmodified JVM applications in this disaggregated architecture, and the way they do it is that the heap of the main process still sees a contiguous virtual address space. However, behind the scenes, there's mappings that map this into partition spaces across the various memory servers that contain the memory for this application. And what the authors are proposing for garbage collection is that you offload the main tracing activities out to the memory servers. But when you want to move objects, you have to still pause the computation on the CPU server so that you don't end up in an inconsistent state where the CPU server and the memory server have different addresses for the same object. And the final challenge that we have to look at is how to properly swap data. Now, the Linux kernel has some existing mechanisms that let it use remote memory accessed over InfiniBand or NVMe over a fast network and use it as swap space. The problem is that this swap architecture is not aware of the language runtime, so it doesn't work in concert with what the language runtime needs. And what the authors are doing in this system is modifying the NVMe over the network implementation to support this sort of remote memory management that takes into account what memory the runtime is using and how to swap that. So this diagram over here gives a nice summary of the architecture of the entire system. You can see the CPU server over here. That is your main JVM that's running the application. And this sees one contiguous virtual address space. In this case, you see the actual RAM for this application being split across 3 memory servers. And they call these LJVMs or lightweight JVMs because they're mostly just responsible for garbage collection. You have some local RAM on the CPU server, which they refer to as the cache, but they still map this contiguous virtual address space on the CPU server out to the separate address spaces of each of the 3 separate memory servers. The communication of reading and writing to this remote memory is happening on RDMA over InfiniBand. And there's also some integration with the Linux kernel block device and swap algorithms such that when you have RAM pressure on your local machine, you can swap out some of that RAM to the block device, but that's backed also by RDMA. So let's look at some results. What does the performance look like? The authors evaluate this JVM architecture, which they call Semeru. I had to Google that. That's apparently an active volcano in Indonesia. So they evaluate it on some widely deployed Java applications on the Spark and Flink frameworks. And the baseline is to use an architecture where these systems talk directly to remote memory using NVM over the fast network. And this is where reading remote RAM is very frequently, and it gives you a very high latency penalty. So they compare that kind of brute force baseline to the system they've designed here, where the language runtime works in concert with the kernel and the garbage collector and optimizes memory accesses in a way that harnesses some of the locality of reference. And they have done this evaluation for different sizes of cache, which is the amount of local RAM. So they saw that Semeru improves the performance over this baseline by about 2x when the cache size is 50% and about 3.7x when the cache size is 25%. And garbage collection performance is improved by about 4x to 5.6x depending on the cache size. So that's a pretty significant performance improvement over a baseline which kind of brute forced all the memory accesses and did not know about the access patterns and did not interact with the language runtime that the application was running in. So that was a quick look at a Java virtual machine, which was co-designed with the swap system as well as the RDMA system and the garbage collector, so that you can run unmodified Java applications on a disaggregated architecture. And that's an interesting design point in how to run applications in a disaggregated data center. So I hope you enjoyed that, and I will see you next time. Thank you very much.